Hello everybody, this is Mr. Parker from ParkerMaths.com, and in this video we're going to be looking at some higher GCSE exam style questions on upper and lower bounds. So this 31 marks worth of questions. This video is mostly concerned with applying knowledge of upper and lower bounds in order to solve problems. So make sure you've been introduced to this topic beforehand before you attempt the questions in this video. They are quite hard. They're usually geared towards people who are trying to get an A star or an A at GCSE. And you do need to have a little bit of prior knowledge before you attempt these questions. So it's an absolute must that you know how to round to decimal places and significant figures. If you don't, there's absolutely no point in attempting these questions. Go back and have a look at that topic first. Towards the end of this video, there's some more challenging questions that require you to know about some other aspects of mathematics like speed, distance and time, area of a circle, standard form and surface area of a sphere. So you can still get something out of this video if you don't know everything about these four topics, but it certainly would help if you have a little bit of a grounding in them before you begin. As always, the links down the side here will take you to the individual questions. If you haven't had a go at them yet, you can load the worksheet here. If you're just looking to check your answers, you can use the written solutions. And if you want to revise a different topic, you can click here, go to ParkerMaths.com and have a look at what other revision resources we've got available. If you find the videos going a little bit too slow for you and you're already quite confident with these topics, you can click this cog button, which should be down at the bottom of the YouTube video, and change the speed to either 1.5 or 2. Okay, let's get started then. Question 1. A can of drink weighs 342 grams to the nearest gram. Part A says, what are the minimum and maximum weights of the can? Let's start by drawing a number line. And in the middle of the number line, I'm going to put 342 grams. Now this can has been weighed to the nearest gram. So the next gram up would be 343 grams. And the next gram down would be 341 grams. And what this statement here is saying is that the can's weight is closer to this one in the middle than it is to either of these. So if we put 2 marks on the number line, one here and one here, which are halfway, then our can's weight on the number line must be somewhere between this mark and this mark. And halfway between 342 and 343 is 342.5. Halfway between 341 and 342 is 341.5. So if the can weighs anything less than this, it's going to round down to 341 grams. And if it weighs anything more than this, it would round up to 343 grams, and we wouldn't get 342 grams. So the minimum weight must be this 341.5 grams. Because that would round up to 342, and anything smaller would round to 341. The maximum weight is going to be 342.5 grams. Now that might seem a little bit confusing because 342.5 grams would actually round up to 343 grams. But anything even a tiny amount smaller would round down to 342 grams. Some people for this would put 342.49 recurring because that means 342.499999 with the 9s going on forever, and that would round down. But we're talking about an upper limit, and we're saying anything bigger than this will round up, anything smaller will round down. So that is fine for our final answer. In part B, it says the cans are sold in packs of 12. What are the minimum and maximum weights of a pack of cans? In part A, we worked out the minimum weight of one can. It was 341.5 grams. I'm going to write that here. Now, if we imagine that all of the cans in this pack of 12 are the minimum possible weight, then the minimum weight in total will be 12 lots of 341.5. And we can use our calculator to work that out. We get 4,098 grams. Now the maximum weight we can work out in a similar way. The maximum weight of one can is 342.5 grams. And if we assume that all of the cans weigh 342.5 and there are 12 of them, To get the maximum weight of the pack, we'll do 342.5 times 12. And we get 4,110 grams. Now, if necessary, we could write either of these as kilograms. It would be 4.098 kilograms. That's dividing by 1,000. And this one would be 4.110 kilograms. So we can write our answer either in grams or in kilograms. Question 2. Cases each weigh 20 kilograms to the nearest kilogram. What is the least that 6 cases could weigh? Before we begin to answer this question, I'm going to show you a common mistake. What I often see when people approach a question like this is people say, right, the weight of each case is 20 kilograms. I'll multiply that by 6 because there are 6 cases. That gives me 120 kilograms. And then they say, well, that's correct to the nearest kilogram, so the minimum would have to be 119.5. Because otherwise, it would round down to 119 kilograms. And we said it's 120 to the nearest kilogram. This approach is wrong. Hopefully when you've seen how it's done correctly, you'll see why that approach is wrong. So what we actually need to do is first of all consider the weight of one case. If it's 20 kilograms to the nearest kilogram, then let's draw a number line again. We've got 20 kilograms in the middle. It's to the nearest kilogram, so the next kilogram up is 21 kilograms. And the next kilogram down is 19 kilograms. So the midpoint on the right is going to be 20.5 kilograms. And the midpoint on the left is going to be 19.5 kilograms. So now we know the weight of one case has to be between 19.5 kilograms and 20.5 kilograms. And I'm going to show you a notation now that I'll use for the rest of the questions in order to shorten how I write down the upper and lower bounds. I'm going to put a square bracket around this end and a curly bracket around this end. The square bracket represents that it can be 19.5. And the open bracket represents the fact that it can't actually be 20.5 kilograms. Although if we do use these figures in a question, we will actually use this 20.5 kilograms. So in future questions, I'm going to use this notation without mentioning where it's coming from. So we're interested in the least that 6 cases could weigh. So the minimum for one case is 19.5 kilograms. So the minimum for 6 cases will be 19.5 multiplied by 6. What I'm doing here is taking the minimum weight of one case and saying let's assume all cases weigh the minimum. And that gives us 117 kilograms. Remember when we did the common mistake at the beginning and our minimum was 119.5? Well, if we take the minimum weight of a case to be 19.5 and multiply that by 6, we get something less than 119.5. So this is the minimum value of each case. Question 3. A crane has a cable with a braking strain of 5,300 kilograms measured to 2 significant figures. It is used to lift crates which weigh 100 kilograms measured to the nearest 10 kilograms. What is the greatest number of crates that can be lifted at one time so that the cable does not break? Before we begin doing any calculations to figure out the greatest number of crates, the first thing we're going to do is consider what the minimum and maximum values of the braking strain are and also what the weight of the cases are. Let's consider the cable first. It's 5,300 kilograms to 2 significant figures. Well, let's consider what we mean by 2 significant figures. That really means we're rounding to the second column here. So that's to the nearest 100. So for this particular problem, 2 significant figures means round to the nearest 100 kilograms. So let's try and figure out what the minimum and maximum values of the braking strain in this cable could be. We've got 5,300 in the middle. The next 100 down is 5,200 and the next one up is 5,400. So our minimum and maximum values for the braking strain will be in here, which are 5250 and 5350. So we'll use the notation I introduced in question 2 and I'll say that the minimum value is 5,200 kilograms and the maximum value is 5,400 kilograms. Next we'll consider the crates, and we know that they're 100 kilograms to the nearest 10 kilogram. So we'll put 100 in the middle of our number line. The next 10 down is 90, the next 10 up is 110. So the points in between are going to be 95 and 105. So the possible weights of the crate are between 95 kilograms and 105 kilograms. The next part is the tricky part. In order to be certain that the cable isn't going to break, we are going to assume that the cable can lift as little as possible. So we're going to say that the maximum weight of all the crates cannot exceed this minimum value for the breaking strain. We're also going to take the maximum that each crate could weigh. Now I want to use an example to show you why I've chosen 105 kilograms for this one. Let's say instead we chose somewhere in the middle and we said each crate weighs 100 kilograms. Well, if the minimum weight the cable could handle was 5,200 kilograms, hopefully you could see, if each was 100, that would be 52 crates. But what if a few of them weighed more than 100 kilograms? Because they can weigh up to 105, then the cable would snap. So if we don't want the cable to snap, we have to assume that each crate weighs the maximum possible and assume that the cable can hold the minimum possible. That's the only way we can safely determine how many crates it will hold. So to determine the number of crates, we want to see how many times 105 will go into 5,200. So how many times the maximum weight of the crate will go into the minimum breaking strain. So we're going to do 5,200 divided by 105. And that gives us 49.5 if we do it to three significant figures. However, we can't have half a crate, so the greatest number of crates will have to be 49. Because if we round it up to 50, then that might weigh slightly too much and snap the cable. So the greatest number of crates is 49. Question 4. A boy runs 50 meters at a speed of 5 meters per second. Both values are measured to an accuracy of one significant figure. What is the least possible time taken? The first thing we're going to do is consider what the minimum and maximum distance could be, and also what the minimum and maximum speed of the boy could be. Well, the distance is 50 meters to one significant figure. And the first significant figure is in the tens column. So to one significant figure means to the nearest 10. So here's our number line. 50 meters is in the middle. The nearest 10 downwards is 40 meters. If we go up 10, that would give us 60 meters. And it's got to be closer to 50 meters, so here's halfway. It must be between 45 meters and 55 meters. So we'll write that using the notation we've been using in previous questions. And the speed we know is 5 meters per second. And that's also to one significant figure. In this case, the first significant figure is in the units. So that's the nearest whole number. Let's draw our number line. We'll put 5 in the middle. The next number down is 4 meters per second, and then up is 6 meters per second. So halfway we've got 4.5 and 5.5. So we're trying to find the least possible time taken. To do this, we need to use the speed, distance, time formula, and hopefully you know that speed equals distance divided by time. I'm interested in time. If I rearrange this by multiplying up by time and then dividing through by speed, I get time equals distance divided by speed. If you're not sure about this, you may need to practice rearranging formulae so that you can understand how we get the formula for time. So we know that time is distance divided by speed. But we need to know which distance to use and which speed to use to make the least possible time. Well, one way is through trial and error. Try the different combinations of speeds and distances and see which one gives you the shortest possible time. However, if you think about it carefully, to get the smallest possible number here, I'm going to take the smallest possible distance that the boy could travel and divide it by the largest possible speed. Because when you divide by something, the bigger the number you divide by, the smaller your answer. So we're going to take the smallest possible distance, that's this one here, and the largest possible speed. So we're going to do 45 divided by 5.5. And that gives us 8.18 seconds to 3 significant figures. Question 5. Tim fits television aerials in houses. He buys 100 metres of television cable. Each house needs 10 metres of television cable. The length of cable which Tim buys is correct to the nearest metre. The length of cable needed for each house is correct to the nearest half metre. After working on 9 houses, what is the minimum length of cable which Tim could have left? You must show your working. First of all, let's consider the cable that he buys. We know that he buys 100 metres of cable. We know the length of the cable that he buys is correct to the nearest metre. So, cable bought is 100 metres, and that's to the nearest metre. So if we write down the upper and lower bounds for the amount of cable bought, remember the next metre down is 99, the next one up is 101, we get 99.5 metres and 100.5 metres. We also need to consider the cable used for each house. So it says each house needs 10 metres of cable, and we also know the length of cable needed for each house is correct to the nearest half metre. So each house needs 10 metres to the nearest 0.5 metres. Now this one's a little trickier than the last one, so I'm going to draw a number line to help me figure out the upper and lower bounds. We'll put 10 metres in the middle, which means either side we're going to have 10.5, because remember it's to the nearest 0.5 metres, and the other side we'll have 9.5 metres. So remember, it's got to be closer to 10 than either of these. So halfway is 9.75 metres and 10.25 metres. So our lower bound is 9.75 and our upper bound is 10.25. So we're trying to figure out the cable left after Tim has worked on 9 houses. Well, this is for one house here, and we want the minimum length that's left. To find the minimum length that's left, we're going to start with the minimum amount of cable that we could possibly have, and for each house we're going to use as much cable as possible, which will then leave us with the least amount of cable left over. So if the maximum amount of cable used for one house is 10.25, for 9 houses we're going to use 10.25 multiplied by 9. And that gives us 92.25 metres. So if this is the maximum amount of cable we could possibly have used, then we're going to subtract that from the minimum amount of cable that we could have started with, and the cable left will be 99.5 metres minus the amount that we've used, 92.25 metres, and that gives us 7.25 metres left over. And that's the minimum length that you could possibly have left over after working on 9 houses. Question 6. A circle has an area of 100 centimetres squared measured to the nearest square centimetre. What is the lower bound of the radius? We know that the area of our circle is 100 centimetres squared to the nearest square centimetre. So the next centimetre squared down will be 99 centimetres squared. The next one up will be 101 centimetres squared. So our bounds are 99.5 centimetres squared and 100.5 centimetres squared. If you need to, like in previous questions, draw a number line to help you figure out these numbers. Now for a circle, we know that the area is pi times the radius squared. So if we want the radius to be as small as possible, that means we need to take the smallest possible value for the area. So we're going to assume that our area is 99.5 centimetres squared. That's the smallest possible value of the area. And we'll put that into the formula. We now need to do a little bit of rearranging formula because we need to find out the radius. So I'm going to divide both sides by pi because r squared at the moment is being multiplied by pi. If you're not confident with what I'm doing in these steps, you need to practice your rearranging formulae. So I'm going to say that 99.5 divided by pi, so I've divided the left side by pi. If I divide this side by pi, that cancels out multiplying by pi and I get r squared. To get r on its own and not r squared, I need to take the square root of both sides. So I'm going to do the square root of 99.5 divided by pi. And that gives me 5.63 centimetres to 3 significant figures. Question 7. A coffee machine dispenses 130 millilitres of black coffee into cups with a capacity of 175 millilitres. These values are accurate to 3 significant figures. Milk is supplied in small cartons which contain 21 millilitres, accurate to the nearest millimetre. Beryl likes milky coffee and always puts 2 cartons of milk in her coffee. Will Beryl's cup ever overflow? You must show all your working. Let's start by thinking about the cup. The cup holds 175 millilitres, correct to 3 significant figures. Now the third significant figure is in the units column, which is telling us we're rounding to the nearest whole number. The next whole number down is 174, the next one up is 176. So remember to draw a number line if you're not confident just writing them down. We've got 174.5 millilitres, which is the lower bound, and 175.5 millilitres, which is the upper bound. Next, let's think about the coffee itself. The coffee machine dispenses 130 millilitres of black coffee. And this is also to 3 significant figures, which also means that this is to the nearest unit. The smallest it could possibly be is 129.5 millilitres, and the largest it could possibly be, the upper bound, is 130.5 millilitres. We've also got milk. Each carton of milk contains 21 millilitres, and that's to the nearest millilitre. So the next millilitre down is 20, the next one up is 22, so the lower bound is 20.5 millilitres, and the upper bound is 21.5 millilitres. So before we do any kind of calculations to figure out whether it will fit, it's always useful to figure out the upper and lower bounds of each individual quantity. Now let's think about what's going inside the cup. We've got the coffee plus 2 cartons of milk. So we want to know if the cup will ever overflow. So let's assume we're putting the maximum amount of liquid possible into this cup. That's the best chance we've got of making it overflow. Let's also think that the cup is as small as possible, because that also gives us the best chance of the cup overflowing. So we're going to take the smallest possible cup with the maximum amount of liquid. And we're going to see, is the maximum amount of liquid more than the smallest value for the cup? If it is, that means it's going to overflow. So the coffee is 130.5 plus 2 lots of 21.5, which is the maximum value for the milk, because there's 2 of them, remember. and that gives us 173.5 millilitres. If we now compare this value, we can see that the minimum capacity of the cup, 174.5, is very slightly bigger than the maximum amount of liquid we've got. So will the cup ever overflow? We must answer the question, no, the cup will never overflow. Question 8. Assume the Earth to be a sphere of diameter 12,800 kilometres to an accuracy of 3 significant figures. Land covers 28.2% of the Earth's surface to an accuracy of 1 decimal place. Calculate the lower bound of the area of land on the Earth's surface. Give your answer in standard form to an appropriate degree of accuracy. Let's start by considering the quantities given in the question and find out their minimum and maximum values. So we've got the diameter of the Earth. So that is 12,800 kilometres to 3 significant figures. Let's look at the third significant figure. That's in the hundreds column, so we're rounding to the nearest 100. So the upper and lower bounds for the diameter on the Earth, remember the next one down will be 12,700, the next one up will be 12,900. We get 1,750. And the upper bound will be 12,850. Next, let's think about the land. And it covers 28.2% to an accuracy of 1 decimal place. So we're rounding here this time. We've not done 1 to 1 decimal place yet in this worksheet, so let's do that on the number line. We've got 28.2 here. The next one down is 28.1. The next one up is 28.3. Well, it's got to be closer to 28.2 than either of those. So our upper bound will be 28.25 and our lower bound will be 28.15. Next, let's think about how we would calculate the surface area. The surface area of a sphere is given in the formula book in the front of your exam paper. So if you don't know it, you don't have to remember it, just remember where it is and you can just write it down. The surface area for a sphere is 4 pi times the radius squared. So let's have a think now about how we can get the lowest possible surface area. Well, if we look at this formula, that would mean we would want the lowest possible radius. And to get the lowest possible radius, we're going to use the lowest possible diameter. So we're going to use this value up here. So if the lowest possible diameter is 12,750, the minimum radius is going to be half of that, which gives us 6,375. So we'll find out what the minimum surface area of the whole Earth will be by doing 4 times pi times 6,375 squared. Because we've already got the radius in our calculator, we'll just square it by pressing the square button and then times in by 4 pi. And we get 510,705,155.7 kilometres squared. Remember, it's got to be squared because it's an area. So this is the minimum total surface area for the whole Earth. But we are interested in the lower band for the area of land. And we know that land covers 28.2%, correct to 1 decimal place. So if we want the smallest amount of land, we are going to take the smallest percentage of the Earth's surface that could be covered by land. So to find the smallest possible value for the area covered by land, we'll call it smallest land, we need to do 28.15% of this. Well, to find 28.15% of something in my calculator, I would do 0.2815 multiplied by that number. Remember, to turn a percentage into a decimal, divide by 100. So 0.2815 times 510,705,155.7. So because we have this answer in our calculator already, to multiply it by 0.2815, all we have to do is press the multiplication button and type in our 0.2815. And ANS means the answer to the previous calculation. So that's 143,763,501.3. However, this isn't in standard form and it's not really to an appropriate degree of accuracy. So remember, to turn something in standard form, it needs to be between 1 and 10. So we need to move the decimal point 3, 6, 7, 8 places, and it becomes 1.43 times 10 to the power of 8. I've rounded it here to 3 significant figures. And being as all of the numbers we started with are to a maximum accuracy of 3 significant figures, this is an appropriate degree of accuracy. So I'll put the degree of accuracy at the end, 3 significant figures. And that is our final answer for the smallest amount of land